everyone. Welcome to the summary lecture of week 4. Today we will discuss about what we have so far uh, covered in this particular week, week 4. Then towards the end of this lecture, we will also talk about one very basic example of assignment which you can solve using some example data set, and then we can further discuss about how we can solve the assignment in the next class as well. So, in this week primarily we have talked about a statistical foundation for analyzing climate extremes. We have talked about various different probability distribution functions. We have also talked about why these probability distribution functions are very important for climate analysis. For example, suppose there is a change in the climatic system from the baseline scenario to the recent decades or recent scenarios, or in the future steps also. Then how do we assess what property of let us say temperature, rainfall or different weather parameters has been shifted, whether they have shifted their means, the 50th or let us say median data or median value to the higher magnitude or the lower magnitude. So that means that the 50th percentile events, which are more frequent events, or median events are become more has higher magnitudes, for example, or whether your climate system has, let us say, increased the variability, the variability has been increased in the climatic system, which means your extreme events in the positive direction or in the low magnitude directions as well has increased their probabilities, or let us say the overall data has shifted towards one direction, skewness, or skewed towards positive side or skewed towards the negative side, which means you have different types of extreme events, regular events, normal events. The probability has been shifted or changed. So this is basically shows that when we know about inherent characteristics of probability distribution function of our climate data set, and if we know that there is some sort of stressors in the climatic system in terms of, let us say, human induced system, or let us say climatic change driven system, which is also part of indirect human activities and all, can alter your weather conditions in such a way that the extreme events become more frequent and some other types of events become less frequent, like that. So this gives us a very handful tool to quantify the magnitude of change in your system based on your observed or satellite data set, or maybe we can use reanalysis or projected climate data set as well. So in this particular lecture we will summarize whatever the concept we have covered in week 4, lecture by lecture, and then towards the end we will discuss about the assignment. So in the lecture first lecture of week 4, we talked about what is exactly probability distribution function. We described that the probability distribution function is a mathematical expression of magnitude and their probability densities. We have also discussed about there is a difference between the probability values and the probability densities when you talk about, let us say, histogram, or when you are calculating the probabilities of some discrete events. You can calculate probabilities based on number of events of occurrence divided by total number of events, like that. But when you have data like continuous variable, or the spacing between different bin size is very small, therefore in that scenario we calculate, instead of probabilities, we calculate probability densities. So that is basically gives an idea about what is exactly, it's a transformed value of probability, how it gives you the sense that what is the total probability of occurrence in one particular areas. So, if you let us say if you have a probability distribution function for a known events, or let us say you have some theoretical probability distribution function, if you calculate what is the area under the curve, it will always comes out to be 1, because probability cannot be more than 1. So, therefore, based on these understanding, if we have let us say observed some amount of rainfall, or we have time series data for rainfall and temperature, using those data set you can calculate, or you can fit the probability distribution function, and then you can calculate what is their statistical properties like mean, median, standard deviation, skewness, kurtosis, etc. So, there are different types of probability distribution functions in the climate science. One is called normal distribution, which is a bell shaped curve. Then we have exponential distribution, gamma distribution, Weibull, generalized extreme value distribution, GPT distributions, like that. So, generalized extreme value distribution and GPT we have talked about in the sense of extreme value analysis, where one is primarily used for block maxima approach and another is primarily used for threshold, peak over threshold methods, like that. So, whenever we are fitting a probability distribution function in climate science, we try to look at what is the time series behavior, what is the trend in the time series, whether the time series has some sort of increasing or decreasing trend, or whether it has a certain there is no trend at all, or what is the central tendency, or what is the total variability of the data set. Then based on these input from climate models or different types of data set, we can calculate statistical properties, we can predict what is likely to be happen in the future conditions. For example, we can predict what is the magnitude of 100 years flood return period, magnitude flood for one particular location based on the historical records, or let us say extreme rainfall events as well, or let us say maximum temperature of one particular locations as well. So, these informations are very important to assess different types of extreme events, regular type of events in different parts of the world. For example, if we are using temperature, we can talk about heat waves in a certain region. If you using the let us say discharge of a river system, or water level, or let us say water inundation area, we can talk about floods magnitude or variability across one particular region. Or let us say if you talk about low flows or low rainfall or SPI or SPEI index, like that, we can talk about drought variability in a certain region based on those analysis. So, therefore, the application of the probability distribution function is very important in order to assess the flood risk, rainfall analysis, or different meteorological parameters, for example, wind speed, temperature extremes, etc. So, we have talked about different types of extreme distribution function, which is normal distribution. Sometimes it is used for analyzing the temperature data, because it can also go in the negative and positive direction. Therefore, we can have we can use those quantity, that can also be in negative and that can be also positive at the different time interval. Then we can also use gamma distribution, where we are trying to look at precipitation extremes, precipitation data set, and then we try to fit into the data and then try to find out what is the overall change in the pattern of particular distributions. Then we can also use exponential distribution, that is basically used for low magnitude or high magnitude extreme flows, like that. Then we have extensively discussed about extreme value analysis, extreme value distribution functions, which can be used to quantify the maxima and minima probability of occurrence of floods and droughts, or different types of extreme analysis in different meteorological properties, like that. So, when you talk about distributions, it is essentially a mathematical function, and this mathematical function has some parameters. So, suppose you have data, whether it is originated from observed data or satellite data or reanalysis data or climate projections like that. We gather those historical or future climate data set, we try to fit a certain mathematical expression which is a probability distribution function. When we are saying the fitting of distribution in a data set, we are essentially referring to parameter estimations, because suppose when we are referring to, let us say, normal distribution. So, normal distribution has two parameters and that parameters have number of values, which means the normal distributions can have multiple different types, okay, because of the change of the parameter values. So, therefore, to essentially look at a specific type of distributions, we have to find out what is the exact parameter which will satisfy a particular data set for that particular observations. Therefore, parameter estimation is a very important step which can tell us about what type of specific type of probability distribution functions is suitable for that particular data set. So, we have talked about there are two methods which we can generally use. There are multiple methods, but we have talked about two, that maximum likelihood estimation method, MLE we call, and then we can also use Bayesian parameter estimation method. So, which can also assess the parameters of different values based on prior distribution informations like that. So, once you have calculated the parameter of the distributions using that specific type of distributions, you can calculate the probability of occurrence of different extreme events based on given magnitude of your extreme climate variable. So, you have to provide the extreme values or climate values to the mathematical model, that is probability distribution function, and it will return to your the probability values for that particular data set. So, this is what we had discussed in the lecture 1. In the lecture 2, we have primarily talked about what is extreme value theory. So, when you talk about, for example, annual flood analysis, severe storm prediction, temperature extremes, or there are so many other weather related events or climate related events which are completely dependent upon tail behavior. Tail behavior is basically the tail of your distribution. So, when you are more concerned about the tail behavior of the distribution, which means you are concerning about what is the behavior of your extreme events which has lower probability in your data set. Why it is important? Because it will give you a clue that how frequent a particular magnitude of floods, droughts, extreme events or temperature extremes or heat waves or tropical cyclones like that are occurring in a certain locations, and what is their probabilities and what is their likelihood magnitude. So, this is very important in terms of, let us say, risk quantification, decision making or some sort of mitigation steps by applying information of these types of things. Therefore, in that sense, extreme value theory is extremely important, which is a statistical framework where we can use extreme value analysis such as record breaking temperature, intense storms, catastrophic floods to model these events, and then we can get an information about what is their probabilities and their corresponding magnitudes. So, this is the application in wind speed analysis, flood analysis, heat wave predictions, drought assessment and all. Here we can apply these extreme value theory. Then in the lecture 2 of week 4, we have also discussed about two data sorting approaches, data selection approaches. Suppose we are interested in applying extreme value theory or extreme value distribution in certain data type. First, we have to prepare our data according to that distributions, either the block maxima approach, whether we are assuming there are several blocks and within these individual blocks we are identifying the maximum value. Okay. The block can be your annual maximum series, for example, where you are taking 365 days, 366 days, like that, the annual data set as a block, and for each annual data set you are calculating what is the maximum value. It is also possible we can also use multiple different block sizes, let us say 100 days, 200 days, depending upon our applications. Or maybe if you are working with the monthly data, we can also take 12 months and then take out the maximum month, something like that. So, that is called the block maxima approach, where we are trying to find out the extreme values in different blocks, and then based on that extreme values we fit our extreme value distributions. Why we do this? Because in order to ensure that these maximum values are not interdependent with your neighboring events, which means when you are taking these events separately, we are assuming that process wise these events are independent. Therefore, there is no serial correlation or correlation between, or physical correlation between, different events which we have figured it out. Then another approach is called threshold exceedance, where you assume a certain threshold, and based on above that threshold we find out which peak is crossing above that particular threshold. But in this method we have to make sure that whatever peaks we are selecting, it has to be satisfied that the event should be interdependent and should be mutually exclusive, or whatever the distribution we have taken, it has to be stationary in nature. So, these are the two approaches which basically used to select the maximum or peak data from our whole time series of the data. Once we have identified these data set, we can start fitting our extreme value distributions. What are those extreme value distributions? We have largely talked about two types: generalized extreme value distribution and generalized Pareto distributions. So, in the generalized extreme value distribution, there are three types. One is called Weibull, there is another is called Gumbel, another is called Fritchett, and these distributions are divided based on their shape values. If it is 0, then is Gumbel; if it is less than 0, if it is greater than 0, like that we have divided the GEV distributions. Similarly, we have GPD distributions, where we are using some parameters, and that parameters basically describe whether we have heavy tailed distributions, light tailed distributions, or moderate tailed distributions, like that, and based on that we classify our distribution system, this distribution types. So, if the data set is originating from block maxima approach, we generally use the GEV distributions, and we fit the data into GEV model, and then we try to identify what is the probability and magnitude and their relationship. When we have, let us say, data set is coming from threshold approach, peak over threshold approach, then we try to fit the GPD model, and then we try to find out what is the probabilities and magnitude relationship. So, this is what we do when we try to fit the extreme value theory models. So, the first thing is to choose the block size or threshold, then we have to estimate the parameters, as we have already discussed in the previous slides, that parameter estimation is very important steps that basically gives an idea about what specific type of the distributions we are using it for the data set. Okay. Once that estimation of parameter is done, then we use that model to validate whether the the observed data set, the empirical data and theoretical data are having some sort of correlation between them, whether your model is correctly representing your empirical data set, or let us say the data set you are selected from your some sort of time series analysis, like that. So, this is what we have to consider when we are dealing with the extreme value analysis. So, when we are talking about two different approaches for parameter estimation, for example, maximum likelihood, there are these are the some strong points and potential issues there. For example, less uncertainty quantification, large data set applicability and data driven parameter estimations. When we are talking about Bayesian approach, this is the uncertainty quantification focus, small data set suitable, and we are also try to look at the prior information of the data types. So, this is how basically we try to calculate the parameter from the data set. What is the application of the extreme value analysis? For example, we can try to figure it out what is the heat waves analysis. Suppose we are measuring the temperature or maximum temperature in a daily basis for one particular location. So, for each year you have 365 values, you try to find out what is the maximum value of T max and repeat this analysis for several different years. Let us say you repeated this analysis for 20 years, now you have 20 T max maximum value, and that can basically use for some sort of GEV distributions because you have selected based on block maxima approach. And then you can fit GEV data, GEV model, for example here Gumbel distribution which is a part of GEV, and then you can analyze the probability and magnitude. Similarly, you can talk about you can fit a wind speed analysis based on some extreme value model. You can analyze the flood analysis based on GEV or GPD distributions. Based on that, you can calculate the probabilities of extreme floods and their magnitudes and all. You can calculate 100-year flood return levels and their probabilities like that. Then you can also apply in the drought analysis where you can fit the low flows, low duration or let us say low magnitude rainfall event or some sort of indexes to calculate what is the probability of occurrence of different types of drought events in a different parts of the world, like that. Why we should focus on analyzing the extreme events? Because if we know the probability of occurrence of different extreme event process or different weather parameters, we can have a very informed disaster preparedness, because if we know the probability we can assess the risk, and then once we are able to assess the risk we can inform better infrastructure or agricultural sustainable agricultural activities or public safeties, like that we can inform like in these areas. Or maybe we can, if we know that disaster preparedness, we can basically focus on the climate adaptation strategies, urban planning, emergency responses and all for the long term goal. When we know that okay, what is the impact of extreme events in certain areas, whether they are increasing or decreasing, like that. So, extreme events can give us two important answer: how often extreme occurs and how intense are these extremes are. So, if we know these two informations, we can assess the flood risk, heat waves, drought, infrastructure design based on different extreme events. Then in the lecture 2, we have also talked about the fitting of Poisson distribution, where we are looking at number of data points or number of occurrence of extreme events, rainfall events or temperature maximum events in a certain area, and then we quantify, calculate the Poisson regression or the Poisson distribution parameter, and then based on that we compare okay, what is the parameter of different data sets, so that we can compare okay, in this particular data set we have more frequent occurrence of number of peak events, or in this data set we have less occurrence of peak events, like that. We can compare our data set like that. Then we have also we have discussed about what is the important parameter for analyzing extreme events. For example, we have to be know about the recurrence interval and events count per year, and the combined metrics is we have to look at frequencies, intensity and durations. So, once we know all these three quantity, we can quantify frequency and magnitude relationship at different durations as well. So, this is we can do once we know about these types of different parameters and different types of values or different types of probabilities, a recurrence interval or magnitude accordingly for different types of extremes. In the previous lectures, we have also talked about different softwares. For example, we can use Python, we can use R programming, we can use MATLAB. we can use ArcGIS. So, these are the some of the handful tools which can give you an idea about how we can assess the time series, how we can fit the different types of distribution functions, and we can calculate the probability of occurrence, magnitude, and then we can find out what is the relationship between magnitude and probabilities at different parts of the world. Like, so once we have this analysis, we can compare, let us say, two regions, which region has higher probability of occurrence of extreme rainfall or extreme flooding events like that. ArcGIS is a very useful tool because it can give us information about spatial data points. Using this software, you would be able to map those locations where you have higher vulnerability or lower vulnerability or higher extreme magnitude events or lower extreme magnitude events. You can compare spatially why these areas particularly has low extreme events, high extreme events like that. Or it is also very useful for mapping flood zones, drought areas, some sort of spatial trend analysis as well. So, all these details we have already discussed in the last classes, lectures, and then we have also discussed about what is their importance of analyzing the probability distribution functions, starting from multiple different probabilities to the extreme value distribution function, and why they are very important in order to analyze the extreme values or extreme events across different parts of the world. Based on whatever we had discussed so far in the week 4, we can try to work on, let us say, we can take the rainfall data set and we can find out rainfall extremes based on, let us say, annual maxima, block maxima approach, or peak over threshold. You can draw a threshold and then you can find out how many peaks are there, and then you can estimate what is the probability of occurrence of different rainfall extremes, what is the probability of, let us say, 100-year rainfall extremes, and what is not probability, what is the magnitude of 100 years rainfall events, and different magnitudes which you can calculate for different probabilities. So, you can try using Python or R or MATLAB. So, I will demonstrate this assignment solution using MATLAB tool, where I will try to look at some sort of inbuilt functions which can directly use the data set and basically try to fit the distribution, particularly extreme value distributions like GEV, GPT or Gumbel, Frichet or Weibull. Those distribution we can fit, and then we can try to plot the written level and magnitude plot or probability plot to compare how we can basically assess the probabilities in that. In the next lecture, we talked about primarily the solution of this assignment of week 4. In week 5, we will discuss more interesting content on climate change. Thank you so much for your attention.